There are only 2 topics left for the year. It's crazy. This one here is going to be thermochemistry. In your textbook, it's kind of a combination of chapter 6 and 16, so we'll hit them together. We'll just do one test. Vocab that we should be familiar with: the difference between heat and temperature. Heat is a measure of total kinetic energy associated with a sample of particles. Temperature measures average kinetic energy. Okay, so what does that mean? Total kinetic energy versus average kinetic energy. Well, we've mentioned temperature, especially with gas laws. We looked at little graphs where you could look on your thermometer and the thermometer reads the average kinetic energy of the particles. Now, there may be particles with more energy, there may be particles with less, but your thermometer reads the average amount of kinetic energy. Heat, when we say that it's total kinetic energy, heat depends on quantity. Depends on quantity. The larger the sample, the more particles, the more total heat. A way of kind of thinking about it, let's say I have a giant bathtub, I fill it with water. Maybe the water's at like 40 degrees Celsius. Then I take a small sample of water from that bathtub, maybe a little cup of water. The temperature could also read 40 degrees Celsius. The giant bathtub, the small cup, both have the same average kinetic energy. Particles are moving at about the same pace. But obviously the bathtub with more total particles will have a larger amount of heat. And a way of kind of proving that would be, let's say you want to melt some ice cubes. Maybe 40 degrees is too hot. So you want to cool down the water by adding ice cubes. And you ask yourself, which samples should melt more ice? I think most of us would probably say the large bathtub. Well, yeah, with more particles in the bathtub, there's more total heat. I could melt more ice. Even though my small cup of water is still at 40 degrees, there's less water, there's less total heat. So anytime we want to calculate heat, we're going to need to know the size of our sample, whether that be moles or grams. Other terms that may be familiar to you are endo and exothermic. Exothermic, meaning energy is released. If we calculate an exothermic reaction, we should have a negative delta H. Endothermic, absorbing energy, should give us a positive delta H. Whenever we do these thermal calculations, we'll somehow need to indicate the direction of our energy flow. And so often that's enough. If we say it's a negative or positive delta H, the reader knows if the energy was absorbed or released. You could also just put in the word energy absorbed or energy released. When we talk about absorbing and releasing energy, we're referencing the system and the surroundings. The system is like the reactants and products, all the components of the chemical reaction. The surroundings are just that. If the reaction is in solution, the surroundings are often the water. So I mix two things together, two solutions together. If it's exothermic, the temperature of the water goes up. If it's endothermic, the temperature of the surrounding water goes down. The surroundings could also be the container that you're using, whether that be a glass beaker, or when we do labs here in thermo, we'll use styrofoam cups because they're a better insulator. It could be the air. If I have a styrofoam cup, but it's open to the air, I don't have a lid on it, there could be heat transferred to the air. So the surroundings really are just that. Whatever is surrounding your chemical reaction. And so if we have like an exothermic reaction, energy is released from the system to the surroundings. So the surroundings should increase in temperature. So again, if it were in solution, the temperature of the solution goes up because the surrounding water absorbs the energy released from the reaction. If it's an endothermic reaction, it's absorbing energy from the surroundings to the system. So the temperature of your surroundings, let's say it's water in solution, that's going to decrease because that energy is now being absorbed by the reactants or the products. And the last two, The first law of thermodynamics is just the law of conservation of energy, which we'll look at a little bit in terms of energy transfers. Disregarding any error that might occur, energy should be conserved in a chemical reaction. And the last one, you're going to see this term a lot, enthalpy, is really just a fancy word for energy. Energy flow as heat. So the symbol that you'll probably see is often like just this delta H. And that would mean change in energy or change in enthalpy, heat energy. It's all right, piece of cake. Some basic vocab that we'll want to reference in terms of thermochemistry. Some things that you might be familiar with. A blast from the past. We have used this equation before with specific heat capacity. Do you remember this? Do you remember these cute little graphs that were used for phase changes? This was often like temperature, and this could be like time. As time goes by, we were plotting temperature changes for a phase change. And you remember they looked kind of like this, where the temperature would go up, and then it would plateau. And then it would go up and plateau, and maybe go up again at the end. I'm hoping this rings a bell. Okay, so on these graphs, we would plot like this first section. This represented temperatures where the substance was a solid. Then the first plateau was the melting point. Then in the middle we had temperatures where the substance was liquid. The second plateau was the boiling point. And then finally we'd have all temperatures where the substance is a gas. We did this back in, maybe chapter 10, when we were looking at intermolecular forces and phases. That was a blast, right? It's all coming back to you. When we wanted to do calculations, if the temperature was changing through a particular phase, we used this guy, Q, which you might also use as like delta H, change in heat energy. We could just plug that in as heat. Q equals M, mass. So again, we said when we want to calculate the energy of a particular change, we need to know the mass of the sample. C was specific heat. Specific heat really is the amount of heat it takes to raise the temperature of 1 gram of a substance up 1 degree Celsius. You might recognize water on this chart. We've got some common specific heat values. Water in the liquid phase has a specific heat of 4.18 joules per gram degree Celsius. That unit means it takes 4.18 joules of energy to raise 1 gram of water up 1 degree Celsius. So you start with this specific heat. It's a constant. You look it up on a chart, or it's just given to you in the problem. If you have more than 1 gram, you multiply by your mass. If you want to change the temperature by more than 1 degree Celsius, you multiply by your temperature change. This equation is in the packet. They also tell you what all those variables mean, so if you forget that C is specific heat, it'll tell you. And then it really becomes plug and chug. It's super easy. Be aware that this could be a positive or negative value, and it all kind of hinges on your temperature change. Temperature change is technically temperature final minus initial. So it could be positive or negative, minus temperature initial. If I'm increasing in temperature, it's positive, but if my temperature decreases, final minus initial is going to give me a negative temperature change. And that's okay. So we were able to use this little equation on this graph anytime the temperature did change. So for example, during the solid, liquid, and gas phases, solid, liquid, and gas, these were the sections where we were able to calculate the energy change as Q equals Mass times specific heat times temperature change. Piece of cake. We were not able to use this equation during the phase change. Do you remember during a phase change, the temperature does not change, even though energy is still being absorbed? At a phase change, the energy is being used to overcome intermolecular forces, not just make the particles move around faster. Obviously, we still need energy absorbed. It's just used for a different purpose at a phase change. So, if you were wondering, at the melting point, we used this guy. Do you remember moles times heat of fusion? Heat of fusion was a constant. For water, it was like 6 kilojoules per mole. The amount of energy it takes to melt, 6 kilojoules per mole. And then you just multiplied by the amount of moles you did have. And then at boiling, we used moles times heat of vaporization, which was also a constant. You look it up on a chart, or in an AP problem, they'll just give it to you. Okay, so some of this might ring a bell. Like, we have done some calculations with energy in the past. Here's a new twist. Not that this is really completely new, because I'm hoping that you did this lab in first year chem, or at least something really similar. This is called calorimetry. It's calculations with a heat transfer. You're going to love these. There's a couple in the homework. They're good. Let's see what we have here. 28.95 grams of an unknown metal are added to a test tube. That's supposed to be these little pellets or these little metal beads. 28.95 grams. We'll say that's grams of this unknown metal. The test tube is heated to 100 degrees in a hot water bath. You usually put these metal pieces in the hot boiling water for maybe 10, 20 minutes. So even though you can't really take the internal temperature of these metal pieces, we kind of assume that they take on the temperature of their surroundings. So if they're in hot boiling water at 100 degrees for 20 minutes, we assume that the metal pieces are also 100 degrees. Then we take the hot metal and add it to 100 milliliters of usually just tap water. So in this case, we'll plug this in here. This is maybe just some tap water, 100 milliliters. And the temperature of the tap water is about 23 degrees. We add the hot pieces of metal to the tap water. In this case, they even have a lid. Excellent. And then you kind of stir it around until there's no more temperature change. Now, obviously, the temperature of the water should go up. We're adding hot pieces of metal. And it does. It tells us here that the final mixture has a temperature of 25 degrees Celsius. So in the bottom here, 25 degrees Celsius, that's a mixture of the metal plus the water. And so again, since the metal is sitting in this water for an extended period of time, we'll assume that the metal is 25 degrees and the water is also 25 degrees. So the water increased in temperature by about 2 degrees when we added these hot metal pieces. The metal cools down. The metal starts in hot boiling water and it's going to end in tap water. So the metal's cooling by about 75 degrees. Okay, so here's the deal. Transfer of energy. Assuming no sources of air like heat loss to the surroundings, this should be true. The amount of energy, heat energy, lost by the metal should equal the amount of heat energy gained by the water. Now, one of the major sources of air is heat loss to the surroundings. So you want to do this transfer quickly, because the whole time I have those hot metal pieces in the air, as I'm transferring them to the water, they're starting to lose heat. They're losing heat to the surrounding air. If you didn't have a lid, heat loss. So assuming no air, this should be true. So let's see if we can plug any numbers into this setup. Could I figure out how much energy was gained by the water? We could certainly try, right? Okay, so let's do that one first. This will be heat gained by the water. All right. So we're talking about a transfer of heat. We're not going to boil the water. It's only at 25 degrees. So our equation is Q equals mass times specific heat times temperature change. And it's seriously just plug and chug. The mass of the water, we're going to use 100 grams. Assuming the density of water is 1, which they'll often tell you in an AP problem, and if they don't, you are totally fine using the density of water as 1 gram per milliliter. So 100 milliliters of water should be 100 grams. The specific heat of water is something you can look up on a chart. For example, in the liquid phase, here's the specific heat of water, 4.18. And we should put units in with that too. 4.18 joules per gram degree Celsius. And then finally our temperature change. We have a 2-degree temperature change. Positive 2. If I did this as temperature final minus initial, it's like 25 degrees minus initial, 23. So I have a temperature change of positive 2. You plug this in your calculator, and out pops Q. Q is 836 joules. We'll go like 3 sig figs. That's the amount of energy absorbed by the water. Notice that it's positive. Now you don't have to write a positive in there. If you don't show a sign, we're going to assume that it's positive. This is energy absorbed by the water. The question asks us for the identity of the metal. Well, one way of identifying a metal is to look up a specific heat value. You could find specific heat on like an MSDS sheet. It's something that's constant no matter what the sample size. So for example, on this table, they give us like aluminum and iron. I'm going to guess this probably isn't mercury. Maybe if we could calculate the specific heat, we could look it up on a chart and kind of compare and see what it's closest to. So let's see if we could solve this for specific heat of the metal. And we'll start by trying to calculate the heat lost by the metal. Okay, so again, if there were no errors, we should be able to use this value. The only difference, we need to make it negative. We're going to start with negative 836 joules. It was a heat transfer. The amount of energy lost by the metal should be absorbed by the water. Assuming no errors, that's the same numerical value. The only difference is the sign of the delta H or the Q. All right, so now we plug in values for the metal. The mass was 28.95 grams. We'll leave specific heat as our variable. Temperature change for the metal. Final minus initial, negative 75 degrees Celsius. How did we get negative 75? Well, the final temperature was 25, the same as the surrounding water. The initial was 100. Final minus initial gives us a negative temperature change, which is totally fine. If we plug this in our calculator then and solve for specific heat is usually a positive value. Let's say 0.385, and this would be joules per gram degree Celsius. From here, you'll look it up on a chart. Now, this tiny little chart doesn't have anything close enough, but there's one in the back of your book if you're really curious. This matches up to copper. Boom, identity of the metal, copper. So the point here with these thermochem calculations, or again, they'll call these calorimetry, is that there's a transfer of heat. So if you can figure out the energy gained or absorbed by one, you can use that same amount of energy in reference to another substance.